Welcome to this explainer. Today, we're tracking the really fascinating journey of your Spring Boot domain data as it completely transforms into searchable AI evidence. If you've ever found yourself wondering how your application's raw records actually become something an AI can understand and retrieve, well, you are in the exact right place. We're going to map out the theoretical foundation of AI Fabric. We'll focus on how we selectively project our data, move it safely through the indexing lifecycle, and most importantly, prove that our local semantic retrieval actually works. Here's our architectural blueprint for today. We'll cover Section 1, Data is not evidence, Section 2, Projecting domain entities, Section 3, the Indexing coordinator, Section 4, Local semantic retrieval, and finally, Section 5, Proving vector evidence. Let's dive in. Section 1, Data is not evidence. Okay, we've got to establish a hard boundary right up front. Just because you saved a record in your Spring Boot application, that absolutely does not automatically make it retrievable AI evidence. Think of your domain record as the absolute source of truth. It's locked down, it holds everything, including fields the AI Fabric must never ever see, like internal notes, privilege flags, or passwords. In stark contrast, stored vector evidence is a carefully approved subset, and it's created only after indexing. It combines the record's identity, the approved text, a mathematical numeric vector, and metadata. You could literally have 5 perfectly valid support articles sitting in your database, but you'll return absolutely zero semantic search evidence if you haven't explicitly projected them. Section 2, Projecting domain entities. So how exactly do we safely cross that boundary? Well, we use AI Fabric to selectively project our data, and we do this using explicit contracts. The very first one you need to know is AI capable. You can think of this as a VIP pass. It explicitly tells the framework, hey, this specific domain entity belongs in the AI ecosystem. It identifies the entity type used to resolve all your configuration and vector lifecycle operations. Basically, it's the starting line for your data's journey. Once you're in the door, we use the AI searchable contract. This isolates the actual meaningful prose that we want to search against. Think about a standard support article, right? You would likely mark the title and the body as AI searchable because those fields actually describe what the article means. This is a deliberate data minimization process. We aren't just blindly serializing the whole entity. We're specifically extracting the semantic meaning so the AI can embed it. But we can't just throw raw text at the AI. We pair that searchable prose with AI context. This contract marks your structured metadata. You definitely do not want your stable record ID, your tenant boundaries, or your status flags to be embedded as searchable prose. That just muddies the semantic waters. Instead, AI context ensures this vital structured metadata travels right alongside your vector. This is exactly what allows you to filter results securely and ensure that tenant isolation actually works when you query the database later on. Now, here's something really fascinating about how AI Fabric enforces these rules. You can absolutely use developer-friendly annotations right there in your Java code, which is super convenient. But when it comes down to enforcing strict application policy, an explicit YAML configuration file always takes precedence, period. Where YAML and generated annotation metadata conflict, the YAML wins out. This is a game changer because it empowers your security or architecture teams to express and enforce application policies without having to go in and alter the underlying domain classes. Section 3, the Indexing coordinator. With our data securely projected, we need an engine room to actually process it all. Enter the Indexing coordinator. It handles the entire life cycle through 4 distinct steps. First, it receives the entity and an action plan. Step 2 is absolutely crucial. It decides whether to execute synchronously, right now, or drop it into an asynchronous queue. This right here is why a database commit does not mean instant vector updates. Then, in Step 3, the capability service steps in to extract that approved content we just defined. Finally, in Step 4, it requests a numeric embedding from the provider and stores the vector. Section 4, Local semantic retrieval. Okay, so our data is projected and indexed. How do we get it back using a solid local path? AI Fabric relies on abstract interfaces, which is great because you can swap out providers, but let's look at this fantastic, entirely local stack. We can use OnX for local text-to-vector inference and Lucene for local vector persistence. The massive takeaway here, you absolutely do not need an external cloud API key, and you sure don't need a massive LLM just to prove your semantic retrieval works. It can all be done locally. Let's look at how this plays out at query time. A user types in a natural language question. Boom, the AI Fabric framework takes that query and asks the OnX provider to turn it into a compatible vector. It then simply asks Lucene for the nearest mathematical neighbors in the vector space. That's it. The score you get back ranks similarity only within this specific retrieval operation. It's not some magical percentage of universal truth, and it certainly cannot invent evidence that you never indexed in the first place. Section 5. Proving vector evidence. This brings us to the final and honestly probably the most crucial phase of this whole process. It's the multi-million-dollar architectural question. How do we actually know the indexing worked? We can't just rely on a fluent, smooth-talking chatbot answer to prove our architecture is sound. That's way too risky. We need concrete, observable evidence right at the framework level. So, if you run a search and get 0 results back, don't panic. And please, whatever you do, don't just hard code some generic LLM fallback text to make your UI look nice. Embrace the honest failure. An empty result is actually highly useful operational truth. Let's walk through the diagnostic tree. First, is the source record even ready? Second, did the indexing trigger actually fire, or is it stuck in an async queue somewhere? Third, check the projected content. Did your YAML strip out the text by mistake? Fourth, are your query and stored vectors using compatible embedding models? And finally, check your filters. A missing tenant ID capability will fail closed, which is exactly what a secure system is supposed to do. The real takeaway here is that a bulletproof architecture absolutely demands lifecycle proof. An index is a derived projection, meaning it has to faithfully follow your domain database. You have to prove that creating a record actually makes it retrievable. You've got to prove that updating a record re-indexes it under the exact same stable ID so you don't end up with a mess of duplicates. And you must prove that deleting a record actually removes the vector. Doing one successful search after an initial database seed, that is not complaint lifecycle coverage, not by a long shot. Which brings us to the ultimate ground rule of AI Fabric. You ready? Retrieve the evidence first, generate the answer later. By strictly proving your vector evidence first, using those local tools like Onyx and Lucene we talked about, you guarantee that you are grounding your future RAG, or retrieval augmented generation, in absolute truth. You are completely separating the question of, did we find the right source, from, did the AI summarize it correctly? Those are two very different things. As you gear up to implement this in your own applications, I want you to ask yourself this final architectural question. If 5 articles exist in the database, but no indexing has finished, what exactly should the search return? The answer is nothing. 0 evidence. Understanding why it returns nothing means you truly respect the boundary between raw application data and searchable AI evidence. So take a hard look at your current architecture today. Are you actually proving your evidence, or are you just letting an LLM guess? Thanks so much for joining this explainer. Now go build some undeniable AI truth.